everybody, today we're going to be talking about significant figures. One thing we need to consider when talking about significant figures are the concepts of precision and accuracy. Most of the time they're used interchangeably, but in science it really does make a difference on how we use the terms. So precision means that we can actually reproduce those results over and over and over again. And you always hear your science teacher saying, we've got to repeat those results, you've got to do more than one trial. That's precision. We're going to do this by checking that we can repeat those measurements. So if we can get that same result over and over and over, we know that it's precise. Accuracy, though, is it correct? Does it line up with standards, what we consider to be true or substantiated about something? So what we're going to do is, if we're seeing if something is accurate, is actually check to see if it's still the same using a different method or using a different piece of equipment. So scientists do this all the time when they do peer reviews. They look over each other's findings to see, is this accurate? Does this work in other settings as well? So if we take a look at these four little diagrams here, let's decide which is precise and which is accurate. So if you take the look at the first one, it's hitting the bullseye, and all of them are in the same spot. So we could say that is both precise and accurate. Let's take a look at this bullseye. They're around the bullseye, but they're not clumped. So we would say good accuracy because we are getting near what we're trying to get, but poor precision because we're not getting the same result over and over and over again. Look down here on the bottom. They're all clumped together, but they're not near the bullseye. So, poor accuracy, but good precision. So if our instrument is calibrated incorrectly, could we be getting the same results over and over and over? Yes. But does that mean that the results are accurate? No. And finally, our final picture here. What do we notice? It's all over. This is not a very good game of darts. So this is neither precise or accurate. Okay, the other thing we've got to think about when we're talking about sig figs are, what are those numbers? What types of numbers are we actually looking at? So if it's an exact number, it does not actually affect the accuracy of the number. It is that number. So for example, if I count how many people are in the room, there are that many people. There's no difference or a different way to interpret it. So this is, for example, we would use counting. If you see a 1, just a single 1 in a conversion factor with no decimal places or anything after it, normally that means that that is an exact conversion. Definitions. Anybody think of a definition? For example, 360 degrees in a circle. That is a definition. It's an exact number. So we would not have to worry about that when we are trying to determine if something is significant to how we should round our number. Any inexact number, anything that is not exact, it cannot be just that one thing, it does affect our sig figs. So this is any measurement. Anything that you had to use a piece of equipment or round a piece of data is going to affect your sig figs, because the number that you rounded to, whether it's the tens, ones, hundreds, whatever it is, it matters how you wrote it down because that is being reflected in your data. So just a little bit more over exact numbers. This is a definition, not a measurement. So it has nothing to do with you taking a ruler or taking a graduated cylinder. This is, could you count it, or could you come up with definition? For example, everybody knows 12 inches is 1 foot. That is a definition. So we do not use these for sig figs. And it's kind of confusing sometimes because you want to use a whole number measurement, maybe, but that's not a definition. That is still a measurement. It just happens to be a whole number. So as I already mentioned, 360 degrees is a definition. Okay, accuracy. Why is this even important? Well, sig figs tell us how good our data is. So whenever we took that measurement, how accurate was it? How reliable was that information? So let's take a look at these three things. They each say 100 grams, but what's different about them? This one is just simply recorded 100 grams, but do we really know this place, the ones place, or the tens place, what's there? We know for sure it's 100 something grams, but that's it. Here you see a decimal place, so that's meaning that these zeros must be significant because I've measured the 1, the 0, and the 0, but yet I don't know anything after it. But do I know more information than I did here? Yes, because I now know my tens and my ones. Here I have all the way to the hundredths place. So in this case, does this tell us even more accurate information than the above two? Yes. So I can see that I took a measurement from 100.00. My measurement was all the way to the hundredths place. All right, so let's review those rules. Rule 1, any digits 1 through 9 are significant. So for example, the number 18 has 1, 2 digits. So there are 2 significant figures. So let's take a look at these 2 examples. 456, 1, 2, 3 digits. There's nothing else there, so there are 3 significant figures. If I take a look at this one, 2, 4, 5, 6, 7, yep, those are all digits, and there are 1, 2, 3, 4, 5 of them. So there are 5 significant figures in that number. That means those were part of the measurement. Rule 2. Zeros between sig figs are significant. They are part of that measurement. So for example, if I have the number 102, I have measured the 100s, the 10s, and the ones place. So all 3 of those are important. So if I take a look at my example, I have a 4, that's a digit, so that one counts. I have a 5 and a 6, those are digits, so those count. So any zeros in between are also going to count because they are part of the measurement. So I am going to count these in between. So 1, 2, 3, 4, 5. So I have 5 sig figs. How about this number? A 2 is a digit, a 4 is a digit, a 7 is a digit. So all 3 of those are significant. That means the zeros in between them are as well. So this number also has 5 significant figures. Rule 3. Placeholders are not significant, and this is the one that normally throws most students off. So in this number, I measured this position, but everything else is simply holding that place because what I've done is I've only measured this thousandth spot. That's it. So that's why I have 1 significant figure. Here I have measured the thousands place, but I have not measured the hundreds, the tens, or the ones. So these are not significant. I only know 7,000 something. So this is 1 sig fig. Okay, let's take a look at a few examples. 1800. So I know the 1 and the 8 are significant because that's rule 1. Those are digits. But if I take a look at these zeros, are they telling me anything, or are they just holding the places so that the 1 is in the thousands place and the 8 is in the hundreds place? In this case, there is nothing else after it. There's nothing else there. So they are placeholders. So there are only 2 sig figs. This one, again, my numbers out in front, they're simply holding the places until I get to this thousandths place. So I do not start counting until I get past any placeholders and hit an actual digit. So 1, 2, 3. These are all digits, so they count. Okay, the one exception, and this was on an earlier slide, if you see a decimal at the end of a number, that decimal there is being specific. It's saying that yes, this one's place was taken, that measurement was taken, and it was a 0. So that means that this number is 3 sig figs because the full measurement went to the ones place, and that ones place happened to be 0. So 3 sig figs. Okay, rule 4. All zeros to the right of a decimal and a significant figure are significant. So what that means is I have to have both a decimal and a number before I start counting those zeros. So just every time you come across a number and you work from the left to the right, do I have a number, a digit, and a decimal place? If I do, then any zeros after it will count. So this one I've got a digit, I've got a decimal place, so those zeros are going to count. That means I actually took a measurement all the way to this hundredths place. Okay, examples. I took a measurement of 18.0. I took a measurement to the 10th spot. I've got a number and a decimal, so the 0 does count. So this is 3 sig figs. Here, this is a placeholder 0. It's not doing anything until I hit a decimal. So here's my decimal and a number. So that means now if I encounter any zeros, they will be significant. So 1, 2, 3 digits and a 0 afterwards because of that decimal and the digit. So 4 total sig figs. Okay, let's try some examples. 53,000, excuse me. So we've got a 5 and a 3. Those are both digits, so they count. Now, these zeros, these are trailing zeros, so they do not count. This number only has 2 sig figs. Okay, 0.00890. These are considered our placeholders, so I do not start counting. Here's my decimal, but I do not start counting till I reach a digit. So 1, 2, and now I have a 0, but I've had a decimal and a digit, so that means this was part of the measurement. So this is 3 sig figs. Okay, now if you see scientific notation, always keep in mind that scientific notation is written that way for a reason. It's written 3.0 because that is in significant figure notation. So this one's going to have 2 sig figs. Now if we expanded that out, that means we would have several zeros. So we'd have 3, and 1, 2, 3, 4, 5. We'd have 5 zeros. And so whenever I look at this, if I just look at this number, it looks like 1 sig fig. But this scientific notation is telling me that this 0 was significant. It counts. So occasionally you'll see a line over 0, and that means that it is part of a significant figure count. We measured all the way to this position. Okay, so here we've got some in-between zeros. We've got a 0 after a decimal place, but it's also after a number. So any in-between zeros, numbers after decimal places and numbers, all of these are going to count. 1, 2, 3, 4, 5, 6. Okay, here's that tricky decimal place at the end of the number. That tells us that we measured all the way to that decimal place, so that means we need to count this 0. So 1, 2, 3, 4. Okay,